This is a problem on the boiling water reactor, and it says a nuclear-fueled electric power plant utilizes a so-called boiling water reactor. In this type of reactor, nuclear energy causes water under pressure to boil at 285 degrees Celsius, the temperature of the hot reservoir. And again, that's a much higher temperature than on our normal standard temperature and pressure because it is under higher pressure. After the steam does the work of turning the turbine of an electric generator, the steam is converted back into water in a condenser at 40 degrees Celsius, the temperature of the cold reservoir. To keep the condenser at 40 degrees Celsius, the rejected heat must be carried away by some means, for example by water from a river. The plant operates at 3/4 of its Carnot efficiency, and the electrical output power of the plant is 1.2 billion watts. A river with a flow rate of 100,000 kilograms per second is available to remove the rejected heat from the plant. Find the number of Celsius degrees by which the temperature of the river rises. And I would say that by which the temperature of the 100,000 kilograms that are being put through of the river rises, then because after that, so downriver it has become hotter by a certain amount of Celsius degrees, but then of course it cools itself off, and then before it gets through there, of course it's at its normal temperature. So it's not the entire river that is being heated up by that, but whatever is being pumped through, and that is the 100,000 kilograms per second. Okay, looks quite involved. Overall, what they want us to figure out is a increase in the temperature of the river water. Let's see what we have given. We have given the temperature, the high temperature of the reactor. I'm sorry, not the reactor. The water. And we assume that the problem says that the steam is going to be at 285 degrees Celsius. I think it implies that very well. And then the steam is going to go back to a cold temperature, respectively condenses to a cold temperature of 40 degrees Celsius. Of course, both of these here have to be in Kelvin, so they're going to be 558 kelvins, top of my head, and 313 kelvins is what we need. It says that the plant operates at 3/4 of its Carnot efficiency. So at some point, I'm sure we have to determine its Carnot efficiency and then take 3/4 of that. The electrical output power of the plant is 1.2 billion watts. So that one is given. And then what else is given is that the river has a water flow rate of 100,000 kilograms per second, so mass over time is given for the river. Okay, let's see, how are we going to come up with this delta T here? Well, the river is going to absorb a certain amount of heat. So the heat that goes into the river warms the river, at least those 100,000 kilograms every second. So there's that delta T. And then of course here, that would be simply the specific heat capacity equation, where we have of course the 4,186 is given, and I have to look that up, what kind of units those are. I never remember them, so I just look it up. 4,186 joules per kilograms and Celsius degrees. And then the mass here, well, what is given is not the mass, but the mass over time. So what I can do here is I can divide the left-hand side by time, and I can divide the right-hand side by time. So that means now I have I have here a known as well, and I have a known here, and I have this one here is my unknown, my variable, and this one here is kind of known as well because it's the heat that goes into the river per time unit per second, and that one is determined from the efficiency, which we determine in a moment, and the total output, the power. Okay, so let's do the efficiency next. The efficiency is, of course, for Carnot engine, 1 minus Tc over Th. Okay. Then I have to determine what the Q is that goes into the river, and for that one I actually need two equations. I need the energy conservation, QH equals the amount of work plus QC, and this one here I kind of know from the power. This one here I'm supposed to determine, and this one here I don't have given, but I can kick this out here by using this equation. E equals 1 minus QC over QH. So like that. And when I plug into one of these equations into the other, for example, I can write E equals 1 minus QC over work minus QH. Work plus QC, that's what I meant to say. Because once I plug this in here for the QH, I come up with this here, work plus QC, and now of course I have this variable here, and that work here that is being done is of course the power output of the plant, respectively the difference between it's per second, so that's a connection between the two, and then I do the algebra on this one here. And you can do the algebra yourself. I'm going to just do this here on the side for the next half minute. And in doing so, this is half a minute later, I multiply everything here with W plus QC, and then I do a little bit of algebra on this one here, and I come up with an expression that I believe is not too difficult. 1 minus E divided by E times work. Now again, that is actually not given. The work isn't actually given. What is given is the power output, but of course the power output is joules per second, and they tell us that 1.2 billion watts or joules per second. So I'm going to use that. I'm going to write here that on the left hand side, on the right hand side, that is 1 minus E over E times the work per time unit, and then of course on the left hand side that's QC over time, as I divide both sides by the time. Of course this one here is power, so I can also write it as such, 1 minus E over E times power. And now I recognize that this one here of course is the same as this one here, because that's the heat that goes into the river. So what I do overall is I calculate what the efficiency is. There we go, come up with some kind of decimal. I take that efficiency, plug it in here with the 1.2 billion watts. I come up with how much energy goes into the river each second. Use that in here, and then divide by C, 4,186, divide by the 100,000 kilograms per second, and I come up with a delta T. So for all of these ones here that I kind of circled, that's the calculations you would have to do. And so from that, overall, from these three equations that I just circled, you have to come up with the delta T. You will see that that is a positive number, which would make sense because the river is heating up, and that's going to be in Celsius degrees. It's going to be a few Celsius degrees. Okay, and then of course I forgot one little thing, which is that this one here needs to be multiplied by 3/4, because that's what the problem says. It operates at a efficiency of 3/4 of the Cutnell efficiency. So both of these numbers here, but the rest of the calculation is the same.